Welcome to another Math Club talk. We are delighted to see all of you here during your holidays. Since last year we did not have any foundational courses, so today we will be organizing the first foundational course of 2023. Today's speaker is Saraswata Sensarma of BMath third year. His interests lie in probability. He will be speaking on the topic the probabilistic method, movements and tails. Over to you, Saraswata.
Yeah, thank you. Sorry for the delay. I was having some problems on my end. So, yeah, the screen is visible. So, is the screen visible? Hello?
Yes, it's visible.
Okay. So, let's start. So, the main idea behind today's talk was to introduce some very simple and fundamental inequalities which turn out everywhere in probability. And it is no really background knowledge required for those, but they turn out to be very useful. So, first is this observation that how to bound the tails of random variables. So, one more question: is my mouse visible? It should be. Yeah, never mind. So, now whenever we talk about random variables, if f is the series of a random variable, we always impose this condition that when x goes to infinity, this is 1. In other words, we are saying that the tail of the random variable, this by this we mean the tail probability. The tail probability is decaying. Question is how fast. You can have a random variable with a tail probability which is decaying very slowly, or you can have something where it decays exponentially. The question is, in general, what can we say? So in general, we can't say too much, but for random variables which have a finite expectation, we have the following. So this is called Markov's inequality. It was discovered way back when by Markov. So so all random variables in today's talk will be positive, but I'll keep writing it. So if you have any positive random variable which has a finite expectation, then the tail probabilities fall off as 1 over n. Okay, so the proof is almost as easy as uh, just picturing it, that okay, the expectation is by definition this sum, but for this sum to converge, when we say that expectation is finite, for this sum to converge, each of the terms has to be, so this should go slower than the harmonic sum. That is what this statement is. I've just given a proof here, but so you just take the first few terms, and since this is a decreasing sequence, so you have this result. Again, this is in the discrete setting. In the continuous setting, it's the same thing. You take the integral and you chop off the integral after the first part from 0 to a, and you keep that. So this would complete the. So for any random variable, since this sum or this integral has to converge, this probability function, this function of tail probability, should go to 0 faster than the harmonic sum, and here it should go to 0 faster than 1 over x. So that is the whole point of Markov's inequality. We needed no other extra conditions on x except we just wanted x to be positive, otherwise these formulae for expectations are not valid, and we wanted it to have a finite x. That's all. So this inequality is, as you would expect, is a very crude bound on the decay of the tail. So in fact, almost all random variables that you have, like normal or exponential, Poisson, anything, it decays. All the examples I said decay exponentially. You can have tails which decay polynomial time, but in general, it's faster than 1 over n. So, however, Markov's inequality turns out to be extremely useful in finding other things and giving a basic bound to the tree. So, one example is another inequality, Chebychev inequality. So, we sort of have this intuitive idea that whenever we have a random variable with a mean and a variance, both are finite, then it concentrates around its mean. So if this is the expectation, the mean of x, then the random variable somehow concentrates. This diagram is actually too good. It shouldn't be symmetric and everything, but we have this intuitive idea that it will concentrate. That is made quantified. That is quantified by Chebyshev's inequality. It just says that okay, x cannot be too far from the expectation with large probability. That probability it will be more than epsilon is bounded by the variance divided by epsilon square. So if the proof is again you take this, so this is the same as this. So this square both sides, and this by Markov's inequality is just the expectation of this quantity divided by epsilon square. The expectation of this quantity is by definition the radius. So we have two very basic inequalities, one dealing with tail probability and another one which is dealing with tail probability of x minus expectation x, the centered tail probabilities. In other words, it's capturing the deviation behavior from our mean. These are the Markov and Chebychev inequalities, which are very useful in non of probability. But yeah, now we move on to another sort of an example, which is by the way, are there any questions at this point? Anyway, so we move on to the second part of the second set of inequalities that we'll be interested in. These are called first and second moment method. Why? We'll see soon. So here the point is, let's say x is a non-negative, I should try. This is a non-negative integer valued random variable x, and we are, so it's often called a counting random variable, and what we're interested in is finding the tail. So sorry, what am I saying? We were interested in finding tails, but what we are now interested in are these probabilities. Is x 0 or is x strictly positive? If x is a counting random variable, this is often used to give existential proofs, whether one such object exists or not. So you will see what I mean. But immediately you can see that probability x is strictly positive, since x is an integer valued random variable. That is, if it's positive, it has to be greater than or equal to 1, which by Markov's inequality is bounded above by expectation. Again, if the expectation is large, this doesn't mean a thing. If the expectation is say close to 1 or less than 1 or much less than 1, then this inequality starts making sense. If expectation is a lot larger than 1, it doesn't, gives you no information. So this inequality is called the first moment method. The probability x is strictly positive is bounded above by expectation, but we want a lower bound, not a matching lower bound, that is way too much fast, but we want some lower bound. So to get the lower bound, we use Cauchy-Schwarz inequality. So expectation of x whole square, you can write that as expectation x times the indicator x is positive. If x is 0, doesn't contribute to the expectation anyway, and then use Cauchy-Schwarz inequality to get this. So in other words, probability that x is strictly positive is bounded below by this quantity, the square of the first moment by the second moment. This is the so-called second moment method, or if you just expand it out, yeah. So I'll try to make all the annotations in green so that it's separate from the text. So we have this expression for the variance, and this is using this we get. So we have successfully given upper. By the way, one thing you might note, put it as a remark, that x positive was sufficient. Yes, in the second moment method, nowhere we use that x is an integer value random variable. However, in the first moment method, we did use it in this step, because we use Markov's inequality. We have to first say, okay, this is equal to that. So we have, so this is what we have for any integer valued random variable. If the second moment exists and is finite, and okay, you can demand it to be strictly positive, then this inequality, you can give both upper and lower bound to the probability of x being strictly positive. So till now, are there any questions? I understand it was maybe a bit drab, just inequalities after inequalities, but now we'll get to the fun part of using these inequalities. So are there any questions? Okay, so one simple, okay, I should maybe do this. So how do you interpret the first moment and second moment method? The first moment method is just again Markov's inequality. You are bounding the tail. The tail just happens to be after 1. That's what you're trying to bound. The second moment method, there's a very simple and nice interpretation, is that This your expectation is large. You're sort of centered around a very large quantity. And your variance, this is not the variance, but your second moment, which increases as the variance increases, is not that big. Which means the distribution, if you look at the PMF or PDF, whatever, it sort of looks like this. So it's concentrated about that expectation. Expectation is large. It's concentrated around that expectation, but it's not spread out too much. In other words, the probability of it being zero is very small. So that's how. So if this quantity is so what? Yeah. So what I'm saying is, if this quantity is large, then the probability of it being zero is very small. Okay. So that's how you might want to interpret this second bound method, is like using this diagram. Okay. So now we get to the real fun, the application. So again, these tools, these methods are extremely simple. The first one, so the first two are just giving bounds to tails, and the second two or one, whatever you want to call it, is just seeing when is a random variable strictly positive and when it is equal to zero, and you can give bounds to that. So the first application is a very simple one. In the sense, you consider just x1, x2, xn to be IID exponential lambda random variable for any lambda. I'll tell you what exponential lambda is. So the question is, what happens to the maximum? We know by the central limit theorem, you can talk about the mean, you can talk about what happens to the average of x1 to xn, but what about the maximum? So where does it go? Where is it concentrated? So when I say x follows exponential lambda, I mean it has this CDF. In other words, the tail is e to the power minus lambda. It's the probability that x is greater than or equal to x into e to the power minus lambda. Okay. So now we want to use first and second moment methods to study where this maximum is. Right. To start with any function k, then set up this counting random variable. This will be a standard theme in all of the applications to come, is setting up a counting random variable and then using first and second moment methods on that. Okay. So define this counting random variable Zn to be the sum of the indicators that xi is greater than or equal to k. So it just counts how many random variables of these exceed k. K is a function of n. I'm just not writing k after it. But then the fact that Zn is strictly positive just means that the maximum is larger than k. So that's how we would get bounds on the maximum being larger than k, by giving bounds on this, and we can give bounds on this by first and second moment method. So let's get to it. Expectation of Zn by linearity of expectation, it's just this. And by the way, you might notice the first moment method in all of these cases is just the union bound. So the first moment method is that probability Zn positive is less than or equal to expectation Zn, but that's just the summation of each of the sums is positive. Okay, so that just is, so write it like this: first moment method is simply the union bound in such cases. Okay, so let's get back the expectation of Zn. So, and with p we denote the tail probabilities by p. Again, p depends on k, p depends on n, but I'm not putting that in. It's np, which is n is 1 minus lambda k. Okay, and the second moment, computation of the second moment is like always slightly trickier. This sum now becomes a double sum over I and j both. And when you're summing over I and j both, you have to take two cases out separately. If I and j are equal, then these two indicators are just the same, so they come out separately. And if they are unequal, you put them in a separate, you put them aside. You can, so you need to deal with these two separately. The first one is again just like before, it's NP. The second one, expectation goes inside. However, here is the crucial part: xi and xj, these two being greater than or equal to k, since they are independent random variables, these are independent events. So these are independent random variables themselves, which means that the expectation splits up, and by independence you have two separate probabilities. But the moment you have this, each of these probabilities is p by our problem, so it's np plus n into n minus 1 p square. Okay, so I hope there is no confusion about these computations. But where are we getting at this? So we, using the first and second moment method, we get this inequality. Is that expectation of Zn square by the first moment square by the second moment, that's less than the probability of Zn being positive, that's less than expectation Zn. Put those two values, I've just simplified it. Now, here's the question. Now what was our original question to begin with? We wanted to see where this maximum lies, right? Effectively, we want to choose this function k as a function of n. You best bet the maximum depends on n. You cannot expect to have a bunch of particles and expect a bunch of independent particles and expect them to remain constrained. There will be a few outliers which go very fast, right? So there will be some random variables which take an abnormally high value, even though that's not typical of a single random variable. There will be some outliers in the entire population, particularly because they are independent. So you best bet that whatever this Mn does is increasing with n. Our question is, at what rate does it increase? How big? So if I say take n, I cube n, what happens to this Mn? Okay. So and Kn is our candidate function to check how big this Mn is getting. And what we have done is we have set up this inequality, which is effectively probability that Mn is larger than or equal to Kn is bounded above and bounded below by these results. Let's call them lower of n and upper of n. Okay. Now the question is, what is Kn to get an optimal result? If Kn is a lot larger than log n, in a sense what I'm saying is, if Kn by log n goes to plus infinity as n goes to infinity, then notice un goes to 0 because of this form, which means the probability that Mn is larger than Kn is going to 0. So in general, this Kn cannot dominate log n, right? Overall, then this probability that Mn is greater than Kn would be 0. And the other side is, we want to use this inequality now, is that Kn cannot be too less than log n. If Kn is much less than log n, what happens? Ln is 1. And so the probability that Mn is greater than or equal to Kn is 1. So it's sort of trivially true. Mn is always greater than Kn if Kn is dominated by log n. By the way, I did not specifically mention these meanings of this omega and little o, little omega, little o. Little omega just means this, and little o means the other way, such as Kn by log n actually goes to 0 as n goes to infinity. Okay. So this function, the Kn, we wanted to sort of estimate where our random variable was going, where the Mn maximum random variable was going. This estimating function cannot be too bigger than log n and cannot be too less than log n. It cannot be dominated by log n and it cannot dominate log n. So it must be somewhere in the order of log n. So that we are denoting by theta of log n. And so if you look at this graph of increasing Kn and you just look at this limit, then it's 1 all the way here. And if it's too big, it's much bigger than Kn in order, then it's 0. But if it's in the order of Kn, it has some. So both of these terms are then finite. Un and ln both are finite and strictly this side is strictly positive, which means this has a non-trivial value. It's not 0, it's not 1, it's something in between, and that's where we want to lie. We want to find where this Mn random variable lies. To do that, you just check the places where the CDF is 0. It's not 0, it's not 1, it's somewhere in the middle, right? So essentially what we have got is that this Mn concentrates around log n. So some constant times log n, I should say, but around the order of log n. In particular, for any epsilon positive, we can say that the probability that it will be between some C1 log n and C2 log n is greater than 1 minus epsilon. So we can choose C1, C2 so that this probability is arbitrarily large. Okay. So this was the first sort of example that we wanted to see is how the maximum behaves. Now I should admit that this is not the sort of the cleanest or the best proof for this particular result. The fact that it will be log n can be proven in other ways, probably cleaner ways, but I just wanted to demonstrate the first and second moment method in action, and this was a very simple example. So for instance, you can do a lot more. You can say that first of all, this mn minus log n minus mn actually goes to 1 by lambda log n. This does not this at no place give you the constant in front of log n where it is going to, but you can show that mn is going to 1 by lambda log n, and in fact the difference converges in distribution to a Gumbel distribution. That is something you can show using other arguably more elementary methods, but this was sort of a simple example to demonstrate first and second moment method. And the second one, which is the more important part that I wanted to get at, is that this is not unique to exponential lambda distribution. We started with an exponential lambda distribution, but the only key part that we used was this NP. Okay. So when was NP going to 0 and when was NP going to infinity? That's what we ended up using, right? However, for many distributions, the scale probabilities are exponential. Excuse me, just hold on for one. Yeah. So what was all these convergence divergence behavior, whatever we discussed, it entirely depended on this quantity and this quantity, which are the same quantities. The question is when uh, so if you have a probability distribution where this probability, which is just the tail probability, x greater than or equal to k, this decays exponentially, same results hold. All the exact same results hold. In other words, this also holds. In other words, the fact that having n independent random variables takes up your range to log n is not unique to exponential lambda. It holds for a very large class of distributions. For instance, the normal distribution, or anything with an exponential tail, Poisson distribution, gamma distribution, many distributions. In fact, any distribution for which the moment generating function exists at all points, and so on. So this is sort of a useful thing to keep in mind as well. If you have any independent random variables, the maximum is of the order of log n with very high probability. Yeah, that was the sort of first application of first and second moment method. So please, if there are any questions, let me know now. Yeah, it's hard giving an online lecture. I can't see anybody. So, just confirm whether I'm audible or not. Or just am I speaking to myself?
Yes, it's audible.
Okay, then it's right. Yeah. So I hope this was clear. If not, you can just ask. And yeah. So this is one application of first and second mode method. This counting variation. So we'll give another quick one. Is which will be very related to graph theory, and it will be very relevant to the people who are taking the winter reading project on random graph is okay. So we start with the construction of an Erdos-Kac random graph. So choose any graph. Let G be a graph on n vertices, which you construct as follows. So consider the complete graph on n vertices, and each edge you choose whether it's in your graph G or not, whether it's there in edge set G or not. So you fix a probability P, and each edge is included with probability P or excluded with probability 1 minus. Okay, completely independent of all other edges. So this construction is the so-called Erdos-Kac random graph, and you can ask many things about random graph. So one question is, you can vary this n and p, or ask. So one question you might ask is, when is this G and P connected, or when do you expect it to be connected? Of course, there can arise an instance of the graph where it's not connected, but for what value of p do you expect them to be connected, or for what value of p do you expect a triangle to be there in the graph? That's a 3 cycles to be there in the graph. So we'll try to answer that question, and so that would hopefully lead you to many similar questions which can be answered very similarly. This is sort of where the true power of first and second moment methods are revealed. This is where they're used a lot. Okay, so the question is, for what function of p is G and P expected or not expected to contain a triangle? Okay, so one question you might ask is, what happens? So as n increases, it's a very simple observation, is that as n increases, there are many more potential triangles in the graph. So p, I mean, if you keep the same p and increase n, eventually the graph will end up having triangles. So the question is, so p of n should be something like this. It should be a decreasing function. So this is, we want the critical function above which it has triangles and below which it won't have triangles. Okay, so this p of n will be a decreasing function. I haven't properly defined what Tn is, but by the time we complete this, I hope it will be clear. Anyway, so the question is whether it has a triangle or not. Again, you construct the same indicator random variable. How? Counting random variables. Just take delta 1, delta 2 all the way up to delta m to be an enumeration of all the triangles in Tn. There are n choose 3 triangles, and let's say ai be the event that delta I is in our Erdos-Kac random graph G and P. So as before, you define the Zn to be the summation of indicators of ai. So again, Zn is positive if and only if there exists a triangle in G. So to give bounds to the probability of there existing a triangle in G, it's sufficient to use the first and second mode method, right? So what about the expectation? The expectation is just m times probability of ai. All the ai's have the same probability. And what is our probability? You need all 3 edges to appear, and the edges are independent of each other, which means the probability is p cubed. So it's just n choose 3 p cubed. But think about it, n choose 3 p cubed is going to 0 if p is much less than n, 1 by n. In other words, if what should I say? If limit np is 0 and n goes to infinity, then this is also going to 0, right? In other words, this is the, I'm sorry, yeah. In other words, the probability that the graph will have triangles is actually going to 0. This is the upper bound on the probability, right? So the probability that the graph will have triangles is going to 0 for p smaller than 1 over n. If the function p of n is dominated by this function 1 over n, the graph is not expected to have triangles. Again, if you look at the second moment, so this is why I put up this example. We split the second moment exactly as we did in the first part. However, now this computation is not so easy. These two events are not independent, so you can't write probability I, probability aj separately. It's the intersection, but you have to evaluate this carefully. And this sort of behavior will happen most of the times when you try to use first and second mode methods, it will be the second term which will be the problem. So the second mode method is actually a bit harder to apply than the first mode method. But such is life. What can you say? So the first term is something of the order of n cube p cube. We don't need to worry about that. Second term, so split it into two parts. The part where the triangles, so okay, what is this? This is the probability that delta I. So this event, AI is even that delta I is in there, and AJ is even that delta J is in there. So delta I, delta J either do not share any edges or share exactly one edge because these are different triangles, right? So either they share no edges or they share exactly one edge. If they share no edges, then those two events are independent, and then we can split them up like this. If not, then we cannot split them up like this. And again, note that it doesn't matter what ij it is. If delta I and delta j have no intersection, these values are the same. And again, here it doesn't matter what ij is, and this value is p to the 6, and this value for okay. So either there are triangles, even if by the way triangles share a vertex, these two edges are still independently included or not included. So the if this is delta I delta j, ai is independent of it. Where it's not independent is a situation like this. Yeah. So this is one triangle and this is the other triangle. Now in this situation, 6 edges need to exist for this to hold. So this is p to the 6. In this situation, you can 5 edges suffice. So you need p to the 5th. So all these 5 edges need to be there. So, but now all we want to do is count how many terms are in these summations. So this simply means the number of ordered pairs ij such that delta I and delta j have one element in the intersection. I should have written that, but I wrote it in a bit of short form. Again, how to count this? This is extremely easy to count. If you have so you're counting number of pairs ij says that they share exactly one edge. How many total elements are there? Let's just sum over the edges, right? So given two triangles, they will intersect at a unique edge. If you sum over the edges and you say, okay, I'll be adding all the terms where delta A and delta J intersect at this edge E. In other words, given an edge E, you want to choose two triangles like this. One here, another one say here. But there are n minus 2 choices. So how many pairs of triangles can you choose? N minus 2 choose 2. However, I and j are an ordered pair, so it's twice of n minus 2 choose 2. That's why it is term. And how many edges are there in J? Exactly in 2. So you get this expression, which is that's the best. That's somehow I like the most about this these methods is that you just throw away all constants. It doesn't matter. It's just order n to the power 4. It doesn't really matter. And if you think about so this quantity is of the order of n to the 4th. And what about this? So this is all triangles which do not intersect. Now how many triangles are there? There are n cube triangles of the order of n cube triangles. So there are n to the power 6 ways of choosing a pair of triangles, of which n to the power 4 have an intersection. So that means what is the order of this term? This term is n to the power 6 minus n to the power 4, which is again of the order of n to the power 6. We can throw away all extra terms. So expectation of Zn square, you don't really need the exact value. I did that in the previous example because it was easy to do. I purposely took an example where these are independent events, but even if they are dependent events, you don't really care. And so we have successfully gotten the second moment, and again you check. It's very easy to do that. If P dominates 1 over n, this was that L of n term, the lower bound goes to 1, and then the triangle is in there. So we have this wonderful relation, which by now is, you have seen it a couple of times already, is that a triangle is in GNP the probability of that is 1 if p dominates 1 over n, is 0 if p is dominated by 1 over n. So such a function 1 over n is called a threshold function, and this is extremely common in the theory of random graphs. In many probability processes, you see it almost everywhere, and this is called a threshold function for the property that GNP contains a triangle. Similarly, you can have threshold functions for anything. You can ask, okay, what about this graph? This is a 4-click. Okay, sorry, not this. This is a 4-click, a complete graph on 4 vertices. What is the probability this belongs to GNP? As it turns out, the threshold function, threshold, what is the setting of threshold? Threshold function is, in this case, would be n to the minus 2/3, and so on. So one thing you might try is to find threshold function of all such small graphs, complete graphs, whether they are there or not there in GNP. Okay. So yeah, that's the end of this example. Are there any questions, doubts, questions, anything? I'll take a sip of water. Yeah. So most people here are first years, and we have seen quite a bit of number theory. Actually, the number theory course we've had is very rigorous. So I wanted to kind of honor that with giving an example from number theory. So you have this. So given any number n with a prime factorization, let Vn be the number of distinct prime factors, and we would like to estimate for a given number how many prime factors are there. Does anybody know what the answer is? So has Professor Ramjan told you something like that? If not, not a problem. So you would like to find the average number of prime factors for a given number n. Okay. So look at this. So this is a very simple double counting argument that if you are summing over, so fix any x positive, and you sum over all numbers. I should say this. I'll not say this on and on, but whenever I write n, I mean a natural number. Whenever I write p, I mean a prime. Okay. So you are summing over all the v's, but this is effectively just this. You're just counting how many primes divide n, but then using the wonderful power of double counting, you swap the two sums, and as it turns out, you get this quantity. And there's this theorem which I believe you all know. Theorem that summation 1 over p of p being less than x is around log x plus some constant c plus something plus little o of 1 over log, and it doesn't matter. We'll be clubbing this entire thing into an order 1, but using this you get this. So in other words, if you write down the average, this is, so for arithmetic functions, this is how, oh, I need a mistake here, n. For arithmetic functions, this is how one talks about the average, because they jump up and down too much. So if you take something like the totient function, for primes it's very large, it's p minus 1, but for very highly composite numbers it's much smaller, right? So you can't really expect to get a good estimate unless you average things out. So this is sort of the way you average out arithmetic functions. So, and if you consider the average of this arithmetic function, which is the number of distinct prime factors, you get log x plus order 1. So the average order of Vx order is log x, right? So if I just give you a number, the number of prime factors is expected to be log of that number. Okay. But the question is, this is the average from 1 to that number. What This is the average all the way up to from 1 to say x or m, whatever. So what if I want sharper estimate? What if I want how many times is this bound sort of violated? How many times I don't get close enough? Because not always. It's an arithmetic function, it will jump up and down very rapidly. So in particular, if you just have a prime which is very big, it will be 1 and not log p. Right. So that is the question which bugs us right now. For that, we get to a theorem of Hardy and Ramanujan, two people you might have heard of. And so the theorem goes as follows: fix any delta positive, then the number of natural numbers which sort of for which this Vn is much bigger than log n in a window of, okay, I should, so this difference Vn minus log n is very large, larger than log n to the power 1 plus delta is small. Little o of x just means that proportion with x is going to 0. So little o of x is any function. I know this is a bad notation, goes to 0 at x plus infinity, but I'll write it anyway. So o of x is any function which satisfies this property. Okay. In particular, if you just write it differently, because this was true for any arbitrary delta positive. So if you have any function gn which is going to infinity arbitrarily slowly, it doesn't matter how slowly, you can take 50 logs and then an n, it goes to infinity arbitrarily slowly, then this inequality is satisfied only by very few numbers, only by little o of x numbers. So the proportion of numbers satisfying this property is going down as n goes to infinity and is going down to 0. Okay, so was this clear? What I sort of meant, I might have gotten a bit jumbled in the notation, but this is what I meant. So in other words, you can kind of say this is something that it is Vn concentrates around log n in a window of square root log n. This is often a statement made in convergence results, and this is exactly what we mean by that. All right. So, but this is sort of screaming for a probabilistic interpretation. So if you have xn which is uniform from 1 to n, then just saying that the proportion of things satisfying is little o of x just says that if you have xn which is uniform from 1 to n, then probability of Vn minus log n being greater than or equal to Gn goes to 0 as n goes to infinity. Right? And this should scream Chebychev's inequality to you, because this is exactly the form in which one likes to use Chebychev's inequality. And as it turns out, so this probabilistic interpretation was somehow missed by Hardy and Ramanujan. They gave a more number theoretic proof, which proved this only. It didn't prove a whole lot more, but which was quite a different argument. But later on, when this probabilistic interpretation was sort of observed, it takes 30 seconds to observe, but it sometimes requires a shift in thinking. So once this was observed, Turan, whom you might know from combinatorics, gave a very simple proof of this result, and that is what I wanted to share with you. So, and the proof goes as follows. So you just first fix an n and fix m to be n to the power 1/3. It doesn't, this 1/3 really doesn't matter. To be honest, you can just fix it as 1 minus delta, 1 minus something small. 3 is my favorite number, don't blame me. So, and then you define this counting random variable again in the very way we work with all moment method. We define a counting random variable like this, but here we won't be using moment method, we will be using Chebychev method. So what is this doing? This is effectively counting how many primes up to, okay, so let's have this number n from 1 to n, and this is say cube root of n. So this is just counting how many primes up to cube root of n divide n. Okay. Now note that you cannot have two. So, but Vn minus 3 and Vn, so this Zn, the number of primes less than cube root of n which divide n, this inequality must be satisfied because there can't be more than 3 primes here. The product will be larger than n. So effectively bounding this random variable is the same as bounding Vn. It doesn't matter since they're both increasing, so it won't matter. Okay. So if we can prove this result, instead of Vn we put a Zn, then we'll be done. Okay. So, well, let's give it a shot. What is the expectation of Zn? Expectation of Zn is simply the sum of probabilities that P divides n. Now, what is our randomization? Our randomization, we have just taken Xn to be uniform over 1 to n. Oh, there's actually a mistake here. It should be P divides Xn. Yeah. Just a second. Yeah, I think everywhere it should be P divides Xn because n is not the quantity that we're choosing. Oh no, I think it should be n. I'm sorry. I'm sorry. This is fine. But if I keep it like this, it's not even a random variable. So yeah, I'm right. This should be Xn. Okay, so I'll have to change it. So P divides Xn. But anyway, this is the probability. This is not probability of P given Xn. Okay, this is just the probability that P divides Xn. But that probability, Xn is chosen from 1 to n, right? So if it's chosen from 1 to n, how many numbers less than n are divisible by P? This. And the probability that Xn is that particular number is 1 over n. So this is again by the Merton's theorem, it's log n plus order n to the 1/3. It doesn't matter. The second part, there's a mistake. I'm sorry. This should be order 1 over n. Then this is order of n for minus 2/3. Because order n to the 1/3 with respect to log n definitely does matter. That is the dominating term. But anyway, so the expectation is around log n. Exactly what we wanted. But what about the variance? We want this to be the variance. Or sorry, we want this to be the standard deviation, the square root of the variance. And then we'll be happy. But what exactly is the variance? The variance of Zn splits up into two parts. So the variance part and the covariance part. Right? The variance, the summation of the variance is it's quite easy to do. It's the variance of this indicator, which by definition is expectation minus the expectation squared, which is 1 by p minus 1 over p plus little o plus capital O of 1 over n. And if you just sum over the variance, you get log n plus 1. So we are happy, but we're not sure whether this term, this covariance term, will ruin it for us. So if we compute the covariance of indicator whether p divides n and indicator that q divides n, these two random variables, we compute the covariance, and then this expectation, then this is just covariance xy is expectation of xy minus expectation x, expectation y. But expectation of xy, if you take a product of two indicators, you get the intersection. So this is just the indicator that pq divides n minus these two indicators, and now you just replace them. So the expectation of indicator is just a probability, and you replace them as we did before. You get this bound. So this covariance cannot be too large. In particular, it's bounded above sort of by n times 1 over p, or 1 over p plus 1 over p, and which means that the summation of all such covariances, it's like this: 1 over n comes out, and 1 over p plus 1 over q. but we are summing over both P and Q, and there's an equal to M. So this inequality gives you this. So using again Merton's theorem, I'm not elaborating, but this I guess is direct. So which is going to be? Now this is why. So you might wonder, why did I, instead of taking the sum over all, where did I do it? Yeah. So why wasn't this the case? Because of this step. Now even by replacing this n, instead of summing over all n, if I just summed over all m, this is fine. Why? Because it does not change the expectation. The expectation, I sort of tricked you guys there. Maybe not tricked, you guys know it probably. Log m. This should be log m, but log m is log n plus order. Is just log little n plus O of 1, because n to the 1/3 and n have the same log n. So, and that contributes extra O of 1 to it, but that doesn't matter. Okay. So that is why choosing, so I was free to sort of choose m as whatever I want, any power of n I want, because neither does it change this Vn, nor does it change the expectation. What it does is it sort of helps you at this step where this covariance has to go to 0, because m is order of n to the 1/3, this term is going to 0. In other words, the event that I is dividing n, so p divides n and q divides n, again it should be xn. Whenever you want to see a random variable, you just replace n by xn. These are almost independent events. The sum of the covariances is going to 0, and that sort of is our intuition, right? So if you have the probability of being divisible by p is 1 over p, the probability of being divisible by q is 1 over q, the probability of both of them happening is 1 over pq. So they, by this definition, they should be independent events, and that is what we see here. So it's not really a surprise that the covariance term vanishes in our case, which means that the variance of Zn is just this. In other words, we have the Chebychev inequality. So if you remind you that this was the Chebychev inequality, greater than epsilon is less than equal to variance by variance of x by epsilon squared. In other words, if I just put the variance inside, instead of writing epsilon, I just write square root of variance times epsilon. This is less than equal to 1 over epsilon squared. Yeah. So that's it, and that gives you the result. And instead of epsilon, you have gn, and this is 1 over gn squared, which goes to 0. However slowly gn goes to infinity, which completes. So, however, the question, if you go all the way back, the question didn't look very probabilistic. Turning it into a probabilistic statement enabled us to use this first and second moment method, which gave a quick proof. So this is often this sort of a shift in mindset is often required in mathematics, where you take a problem at hand, you take it to some other sort of area of mathematics, and the techniques used there are different, so you get a fresh perspective on a problem. And in fact, you just don't get a fresh perspective, you get new results, in the sense that this entire thing now begs us the question, what happens to this? So you had this Chebychev inequality. We know this is the mean and this is the variance, but can we have something nicer? So is there something which is lurking, which is related to the convergence of this random variability of xn? And as it turns out, there is that this Erdos-Kac theorem is that v of xn minus the expectation divided by the variance. You just normalize this v of xn, it goes to normal 0 as n goes to infinity. This was proven, I believe, in 1940 by Erdos and Kac paper, and in that paper they actually published a more generalization, is that if you have a strongly additive function, whatever that means. You know what additive function is. Strongly additive just means that f of p to the alpha is f of p for all alpha. Now, so there you can again define these quantities a of x and b of x, which in our case is exactly the quantities that we got, and b of x is going to infinity as x goes to infinity, then this result holds. So this is sort of a story of how a simple result in number theory, which is slightly complicated to prove, can be probabilitified, and there it leads to more sort of beautiful results and so on. So the story behind this theorem, this Erdos-Kac theorem, is Kac was giving a lecture in 1939 at Princeton University. He was giving a lecture, and Erdos was in the front seat dozing away, and he said that okay, Kac was saying that this seems to be the case, but nobody has been able to prove it yet. And by the end of the lecture, Erdos has just raised his hand and said that okay, I have proof. And then later they collaborated to generalize it to this result. So that's about it for me. If you have any questions, please let me know. Thank you so much. Hello? I'm audible? I'll stop the screen share.
Okay, so does anyone have any questions?
By the way, many of the references are quite standard, so you can find some of them. So there's one book called The Probabilistic Method by Allen and Spencer. It's a very famous book. You can have a look at that. Or there's another book called okay, actually have it just a second. Share again. Yeah, so there are these books. So there's this book called The Probabilistic Method by Allen and Spencer. There's another book called Modern Discrete Probability by Sebastian Roch or Roche, I don't know. And the last example was taken from An Introduction to the Theory of Numbers by Hardy and Wright. And you can find individual notes on Erdos-Kac theorem everywhere on the internet. So sort of, so this proof by Turan was one of the first proofs which showed how the techniques of probability and combinatorics can, I mean, I shouldn't say it was the first proof, but one of the proofs which sort of started this idea of probabilistic number theory. It was there before, but this sort of showed its usefulness because some ideas are a small change in an idea in one theory is not the same as a small change in idea in another theory, even if the theories are equivalent. So, yeah, I maybe getting a bit too philosophical. Let it be. But so this was sort of the turning point, and after this, gradually people started picking up the idea of probabilistic proofs in number theory after this proof by Turan. And of course, Erdos did a lot to popularize probabilistic methods in all branches of mathematics. He is the father of using probabilistic methods in modern mathematics, and so this was at the time where these ideas were being popularized, and today they have become completely mainstream. So, yeah, that's it. That's if there are any questions, let me know. Yeah, this is another the book shared by Vikram is another very nice book that also has many probabilistic proofs and so a lot of nice references on probabilistic number theory without going in too much detail about either probability or number theory. So it's a very good book for a first reading. Very nice.
So, are there any questions?
Yeah, I guess we can stop it here.
Okay. Thank you, Shashwat.
Thank you so much for having me. Goodbye.